Okay, so let's pick up where we left off. We were talking about implicit differentiation, and we had done this problem right here. And the basic idea was we treat everything as a differentiable function of x. We differentiate both sides of the equation and treat everything the same, carry out the chain rule on every one of the variables, and we treat y as a differentiable function of x so that we get this dy dx, and then we solve for that. Lots of algebra here, lots of applying the differentiation rules that we've learned to new types of functions. So let's take a look at this problem right here. This is a good problem because, again, it illustrates that we're treating everything as a differentiable function of x. There's some nice uniformity to this. I'm not going to write dx again, but we'll at least talk about that and show why it would be 1. So let's take a look at x squared. We'd find the derivative of that with respect to x. That's going to be 2x. Then this next part right here, how do I find the derivative of x times y? Product rule. So I'm going to think of this as the first and that is the second. So it's going to be plus. And whenever we do a product and we've got more than one term, it would be a good idea to put this in parentheses. Okay. Now there's a plus there, so it's not going to make that big a deal. But then we're going to do the first times the derivative of the second. So that's going to be the derivative of y with respect to x, plus the second times the derivative of the first with respect to x. So we could write dx. We could write 1, but the derivative of x with respect to x is 1, so we're not going to write that. Any questions there? Plus 2y, and do we just leave it like that? It's got to be dy dx, okay? Found the derivative of the outside function. The outside function is squaring. That's going to be 2 times that same thing raised to the first power times the derivative of whatever the base was. In this case, it was a y. So that's dy dx. And what's the derivative of 3 with respect to anything? 0. Okay? All right, so here's what we've got. We've got a plus there, so I'm going to go ahead and remove that set of parentheses. Wasn't technically necessary for that. And then I'm going to collect the dy dx's on one side. And I could take the time to write this. Move this other stuff on the other side. That's going to be minus 2x and minus y. Okay. I have to put these together so that there's just one dy dx. So sometimes it's kind of nice to factor it out and collect them at the same time. You're going to get dy dx and then x plus 2y. And then over here we're going to have minus 2x minus, just minus y. And then we finish this off by dividing, of course. So we end up with dy dx is equal to negative 2x minus y over x plus 2y. And that right there is the answer. So this is another one of those, and this typically happens with implicitly defined functions, is not only does the point that we graph depend on both x and y, of course, but its derivative, the slope at any particular point, depends on both x and y. And most of the time, implicit graphs, at least most of the ones that we deal with, they're not going to be functions. And that's why, like when we had that circle that we graphed last week, that's why we needed both the x and the y to determine what the tangent, the slope of the tangent was at any particular point. Okay, any questions on that? Easy enough? Okay, let's take a look at the next one then. This uses that last derivative that we found. Okay, and this is problem number 27 from your assignment, or at least it's like one in the textbook. Same function that we did up above. It says verify that 1, 1 is on the graph. Calculus or pre-calculus question there? Definitely pre-calculus. All they're asking you to do is plug in a 1 for x, a 1 for y, see if it makes the equation true. If it does, it's a point that's on the graph. And that's pretty easy to check. You'd get a 1 here, a 1 times 1 here, and a 1 there. Add them all together, you get a 3. So that answer is definitely a yes. We've verified that. And then it says determine an equation of the tangent to the curve at 1, 1. So we need a point, which we already verified is on the curve, and we need a slope. So we're going to need to evaluate dy dx at 1, 1. So we're going to take this right here, and we're going to plug in a 1 wherever there's an x and a 1 wherever there's a y. So I'm going to have a negative 3 on the top and a 3 on the bottom. So that means the slope is negative 1. Now, did I make any little arithmetic errors or anything like that? So as ugly as this derivative is, it's the same as the ones that we were finding earlier on in this course. We need a point, and we need a slope, and we can come up with the equation of the tangent line. And I'm going to write it like this. I'm going to write it as y equals, I'm going to write it as f of a plus, well, let's see, we wrote it this way, didn't we? X minus a, and then plus f of a. You wanted to think of it that way. This isn't a function, okay? But this is going to be the slope, -1, x minus 1, and then plus 1. That's in a format, you could throw that in a calculator. Any questions? Can you get your calculator to graph this? If you had one of those with a computer algebra system, maybe, what are those, 89s and TI Inspires, they probably would graph this. There are free graphers that you can get on the internet where you could throw that in and you could see what it looks like. In fact, a lot of the graphs that I make on here, I just use a free grapher that I got off the internet. Yeah, you put the calculator or the computer or the program in what you call explicit mode, and you literally type that in. So instead of putting like y1 equals, you just type in an equation, an implicitly defined equation, and it graphs it for you. Okay? Yeah. What's that? Sure. Yep. Yeah, they're pretty cool. I use one called WinPlot. It's been around for a long time. It's relatively easy to use. It also does three-dimensional stuff, which is kind of cool. That might come in handy in Calc 2. I think they use Maple or Mathematica. You can also use Wolfram Alpha. It'll graph some pretty cool stuff. So let's take a look at this example right here. Although we haven't got much use for the second derivative yet, we have talked about it. We know that if you've got a position function and you find the first derivative, you get velocity. And if you find the derivative of velocity, you get acceleration. Okay? In Chapter 4, we'll talk more about what we can use higher order derivatives for. And you'll study higher order derivatives a lot more when you're in Calc 2. But for right now, we just want to find y double prime on this particular one. So let's think about how you do that. And I mentioned last week, I'm not a huge fan of using the prime notation just because I find it harder to keep straight. I mean, if I have a dy dx, I know that's my derivative. I never confuse it with a y to a certain power or something like that. But if you want to use the prime notation, be my guest. So in order to find the second derivative, we'd have to find the first derivative, right? So this we already did. We already found that dy dx equals, what was it again? I think it was, wasn't it negative 2x over 2y, so it was negative x over y. Flip back on that previous page, isn't that what it was? Isn't that what it was? Okay. Do we need to run back there and take a look at that? Okay, this is the first one that we did. Let's see, we did it right here. So we did derivative of the outside, left the inside alone. Derivative of the inside was dx dx, so that just turned into a 2x times 1. Derivative of the outside, left the inside alone, times the derivative of the inside, dy dx. So that turned into a 2y dy dx. And then, of course, 0 over here. Move that over, divided by 2y. So we got negative x over y. Okay, it's about as simple as it gets for implicit differentiation. Good? Okay, so how do you normally find a second derivative? You do the derivative of the derivative. So let's just find the derivative here. Let's just start this process over again. So if I were to find, and if I were to write it in this notation, remember it's d squared y dx squared. I've got to find the derivative of this function right here. Well, that function is a quotient. So I've got to use the quotient rule to figure this out. So here's what we do. I'm going to do the bottom times the derivative of the top with respect to x, so that's going to be a -1, minus the top times the derivative of the bottom, so that's going to be dy dx. Derivative of the bottom, bottom's y, derivative of y with respect to x is dy dx. All over the bottom squared, so that's going to be y squared. Any questions there? Well, we're done with the calculus, but we really ought to clean this up just a little bit. I mean, there are a couple negatives floating around. It would be nice to take care of that. And there's this expression right here, dy dx. So what we have is the second derivative defined in terms of x and y and the first derivative. So what do you think we ought to do with this guy right here? Substitute what the first derivative equals. Okay, so here's what we're going to have. We're going to have negative y plus x times negative x over y squared. And then again, from here on out, we're just cleaning this up and making this look nice. So let's think about this for just a second. We're going to have negative y minus x squared over y squared. And however you learned how to simplify complex fractions is fine as long as it works. Here's what I'm going to do. I'm going to get a common denominator here. I'm going to write this as one single fraction. So this one single fraction is negative y squared minus x squared over y squared. And then remember, if you've got fractions in a problem, you might as well think of everything as a fraction. So that denominator is a fraction. And then I'm going to flip that over and I'm going to multiply. So I'm going to multiply by 1 over y squared. So I end up with, let's see, negative y squared minus x squared over y cubed. Is that right? Any questions? Okay, so if you need to find the second derivative of an implicitly defined function, you just go through and do implicit differentiation again. Because normally, if you have an implicitly defined function to start with, okay, this derivative is also going to be implicitly defined. Okay, so you're just going to do it twice. Any questions there? Okay. I'm sure the second derivative has some meaning for an implicitly defined function. Probably in physics or something like that. Luckily, we don't have to deal with anything like that in this course, yeah.
So when finding the second derivative, will you always have to substitute
Yep.
dy dx?
Yeah.
Always?
Yep.
Okay.
Yeah. Unless by some strange fluke there's no y in the first derivative. Because if there's no y in the first derivative, there's going to be no dy dx. Once we differentiate it again. Okay, but then it would be just a regular old function like we're dealing with. Okay, we probably wouldn't do it implicitly. Questions? Okay, let's just do a quick reminder of this problem right here. We did this one implicitly at the beginning, and the way we did this was the derivative here is 1. The derivative of sine y was cosine y dy dx. So we got dy dx equals 1 over the cosine of y. And then we came back and we said, well, wait a minute, I could take this and I could write this in terms of another function. I could solve this for y. So we could have y is equal to the sine inverse of x. And then we get 1 over cosine sine inverse of x, which is an expression that we can, if I've got an inverse trig function, and then I take a regular trig function of that inverse trig function, they do somehow undo each other to some extent. Like this one right here, we're going to plug in a ratio, we get out an angle, and then we take the cosine of that particular angle. Okay, remember that picture that we drew last time? So we ended up with this problem right here as dy dx equals, it was 1 over, right? And then it was big square root 1 minus x squared, wasn't it? Let's flip back up here. This was at the bottom of the second page. This guy right here. Remember that? We even drew a picture for this right up here at the very beginning. Remember how we started that off? Okay. Any questions? Okay. So we actually kind of broached this topic a little bit, but let's just do a quick review of some inverse trig. The problem with the sine function, so if I were to graph this as about as accurately as I can, the problem with this is not a one-to-one function. Doesn't pass the horizontal line test. So what we do in order to make it a one-to-one function so that it will have an inverse is we restrict its domain. So we restrict its domain so that we have all of the range covered like this. So it covers from -1 to +1. All the possible ratios that come out of the sine function are covered, and we make it as close to the origin as possible. Okay? So the domain for this sine function is going to be from -π12 right here to +π12. So this point right here is -π12 comma -1, and this point right here is π12 comma 1. And of course it goes through 0, 0, and so forth. Okay? Now the two-step process for finding inverse functions is we switch the x and y and then we solve for y. So if I were to do that, I end up with y equals sine inverse of x. But let's think about what that looks like. When you switch the x and y and solve for y, you're switching the domain of the original function to be the range of its inverse and vice versa. And you're literally switching everything that deals with x to be dealing with y. So this point right here that was π12 comma 1, on the inverse, I just take the two of those and I switch them. So on its inverse, it would have the point 1 comma π12. So here's 1, here's π12. And again, with a regular trig function, you're plugging in an angle, getting out a ratio. With an inverse trig function, we're plugging in the ratio 1 and we're getting out the angle π12. Okay? So this one right here would be -1 and -π12. And we end up with a graph that looks something like this. And if you tilt your head just a little bit, okay, I just drew a really crappy graph, but it's still going to work. Tilt your head just a little bit. Do they look roughly like the reflections across the line y equals x? They do, okay? So if we found the derivative on the problem above, so if we found that if y is equal to the sine inverse of x, that dy dx is 1 over big square root and then 1 minus x squared. Last week Juan pointed out, well, it shouldn't have an inverse at 1, or excuse me, it shouldn't have a tangent at 1 or at -1, okay? Because if we look at this inverse trig function, what type of slope would we have right here? Okay, we'd have a vertical tangent. It would approach a vertical tangent. And of course, we'd be finding the derivative from the left on that one. Okay, and the same thing happens here. Okay, it approaches, it gets so steep, there's no number that represents how steep a vertical line is, so that's not going to exist. And what else do you notice about these slopes on the inverse sine? Looks like that, and like that, and like that, and like that, and like that. What? They're always positive. And take a look at this expression. You have the number 1 on the top, which is always positive, and you have a square root on the bottom, and we're always taking the principal square root, so the bottom is going to be positive as well. So we're always going to have a positive slope, positive derivative for the sine inverse function. Okay? Does that make sense? Going to put some of your trig together with the calculus that we've learned? Okay, so let's take a look at the next thing, and this is kind of an interesting exercise. So the derivatives of functions and their inverses, okay, if they just undo each other, their derivatives ought to have something to do with each other. Okay, so let's think about this. If y equals f inverse of x, if we were to use some algebra, okay, and I just wanted to have f, and it's just a plain old x here, okay, what would go right there? What would go in that blank? It would be a y, right? Right? Because if I took f of both sides, I'd have f of y here equals just a plain old x there. Okay, so that's how those two functions are related. Okay, and then if I were to use a little bit of calculus on number 1, I can get number 3. So this would be the derivative of y, so y prime should be the derivative of the inverse, and notice the notation here, f inverse prime is how we'd say that, of x. And then it says, now differentiate number 2 implicitly and simplify the expression using 1 and 3. So let's take a look here. It says differentiate this implicitly. So let's see what we've got here. If I take f of y equals x and I differentiate implicitly, and notice that this is any inverse function. There's the inverse function. There's the original function, f. So if I do this implicitly, this would be f prime of y dy dx, right? And over here, whoops, need to find the derivative, so that would be 1. Now, let's see. So if I take this, and I normally solve for dy dx, this is what I get. I get dy dx equals 1 over f prime of y. So we've differentiated implicitly, and I've got this expression right here. So I have this algebraic relationship between x and y, whether you're using the function or the inverse of the function. I differentiated this one implicitly, and I got this expression right here. Very similar to what we had here, right? 1 over cosine y. It was 1 over some derivative with a y plugged into it. And what we did up above is we got rid of that y. So how can we get rid of that? Yeah, plug in number 1, okay? Yep. So this is going to be dy dx equals 1 over f prime, the derivative, evaluated at f inverse of x. It's kind of like where we had the cosine here because it was the derivative of the sine, and then we had the sine in here. Okay. Let's see. It says, following the instructions above will give you the answer to a homework problem. So there you go. The bottom line is derivatives of functions and their inverses have a quasi-reciprocal relationship. Okay. So not exactly reciprocals, but has something to do with a reciprocal. And I've written it here in words, and then we're going to go through and we're going to do this problem up here. So if we're finding the derivative of an inverse, so f inverse prime is the reciprocal of the original function f of x with the inverse function plugged in. So what that means is if you're going to find the derivative of an inverse function, you can find the derivative of the original function, do the reciprocal, and then just plug in the original function. Or the inverse, I guess, is what it would be. So let me show you what happens here. So let's blow this up just a little bit. And this might take a little bit of time to think about and put these pieces together. Okay. The original function on this one is x cubed. Everybody here knows the derivative of x cubed, right? So f prime of x is equal to 3x squared, right? Okay, now, just indulge me just a little bit. Okay, this is the inverse of the cubing function, right? This is the cube root. We already know how to find the derivative of the cube root using the power rule, right? Okay. The challenge here is to make this work, come up with the same answer, but using the fact that these are inverses of each other. So we're not going to find the derivative of the inverse function directly. We're going to do this. Okay. This down here says if I were going to find the derivative of this, I could do 1 over the derivative of the original function. What is the derivative of the original function? 3 something squared. And what is that something that we're supposed to plug in? The inverse function, which is the cube root function. So that's going to be the cube root of x. So if I were to simplify that just a little bit, I'd get 1 over, this is 3 cube root of x squared. Okay, put that underneath rather than out. Let me write it over here. 1 over 3 cube root x squared. Okay, and isn't that what we get if we just differentiate that using the power rule? Okay, and it works that way every single time. So let me show you an example of why this reciprocal relationship is important. Okay, if I were to graph the original function, the cubing function, and let's take this point right here. This point right here is 2, 8. Can you tell me what the slope is at that point? Well, the derivative is 3x squared. What are we plugging in for x? Plugging in a 2. So the answer is 12. Okay, so the slope is 12. Really steep slope right there. So if I were to graph its inverse is the cube root function. Looks like this. What is the corresponding point here? What corresponds here to 2, 8 on the original function if I'm going to graph that point on its inverse? 8, 2. Okay, so let's put the point here of 8, 2. Now, if this has a slope of 12, you want to take a guess at what the slope is right here? 1/12. Okay, so we're going to guess that the slope right here, f inverse prime, but wait just a second. You don't get to plug in a 2, do you? It's not that the derivative at 2 on the original function corresponds to the derivative at 2 on the inverse function. What should this be right here? Should be an 8. Okay? And what should it equal? It should equal the reciprocal, which is 1/12. And let's take a look here. What do I get if I take 1 over 3 cube root of 8 squared? 64. Cube root of 64 is 4. 3 times 4 is 12. I get 1/12. Okay? Kind of a wild relationship, a little bit mind-blowing to some extent, but think about why that would have to be true. Okay? Functions, derivatives of functions and their inverses are very closely related. Okay? They are somewhat reciprocals of each other. Okay? So you can find the derivative of the original function, just flip that over, and plug the inverse into that. And you can do that with any inverse functions. Any you want. Okay? All right. So let's use that relationship up above. Let's figure out what the derivative of cosine inverse is. So the first thing we're going to do is we're going to figure out what the derivative of cosine is. So the original function would be cosine. This is its inverse. What is the derivative of cosine? Okay, so it's negative sine of x, right? So if I want the derivative of the inverse function, I'm going to do 1 over this, and what am I going to plug into it? I'm going to plug in cosine inverse. Okay? So we could say this in words. It's 1 over the derivative of the original function with the inverse plugged in. So if the original function is cosine, and its derivative is negative sine, we do 1 over negative sine, and then we plug in the inverse function. And then, of course, we'd want to simplify that, so let's think about how that would work. Again, this is a triangle represented with the adjacent side being x and the hypotenuse being 1. That makes this side over here 1 minus x squared. And if I want the sine of that little triangle right there, I do the opposite over the hypotenuse. And in this particular case, that's a 1. So I get negative radical 1 minus x squared. Does that look familiar? Yep. Okay. Any questions? Okay. Let's do the same thing for tangent. So the original function would have been tangent of x, which we know how to find the derivative. The derivative of tangent is the secant squared x, right? So if I want to find the derivative here, it's going to be 1 over the derivative of the original function, so that's going to be the secant of x squared. And what am I going to plug in instead of plugging in an x? I'm going to plug in tangent inverse of x. 1 over the derivative of the original function with the inverse function plugged in. Okay, this is, that's not too bad. Where do I have to draw? So if I've got tangent inverse of x, and I put that over 1, I should draw that in first or the fourth. Okay, we don't know what x is. It doesn't really matter. What side is this? Opposite, or it's the y coordinate, right? And this would be the adjacent, opposite over adjacent. So I need the hypotenuse here. What's the hypotenuse? Square root of the two of those added together, right? So that takes care of the tangent inverse of x. I want the secant of that. Secant is? Okay. So this is going to be a 1 on the top. Secant, let's see if it's 1 over cosine. Cosine was adjacent over hypotenuse, so this is going to be hypotenuse over adjacent, is that right? Okay. So that's going to be hypotenuse over adjacent. Just doing it a piece at a time. Through that picture up here, I need the secant, so that's going to be hypotenuse over adjacent, radical 1 plus x squared, all over 1. And then I'm going to square that, so what's my answer? 1 over 1 plus x squared. Okay? Any questions? Okay. So let's think about what these functions look like. Okay. Cosine, we restrict that like this. This point right here is, let's see, that's pi comma negative 1. And this point right here is, I'm going to draw it off to the side. That point right there is 0 comma 1. And we restrict it so that it covers all the proper range. Let's see if I flip that. This one's always a little bit tricky to draw. This point right here would be 1, 0, which would be about right there. And this point right here would be negative 1 pi. So negative 1 pi is going to be somewhere around there. So it looks something like this. Oops. Make that look a little bit better. And again, if you tilt your head just a little bit, does it kind of look like reflection across the line y equals x? What do you notice about its derivative? Always negative. And does it make sense why it's always negative? Okay. It's always going down from left to right. Are there places where the derivative doesn't exist? 1 and negative 1, because we've got that same deal. We've got vertical tangents right there. Okay. Good with that one? Convinced that that's a pretty good find there on the derivative of cosine inverse? Okay. Let's think about what tangent looks like. Tangent looks like this. We have a natural restriction on tangent because one cycle from negative pi halves to pi halves covers all the range. And if I take that and I reflect it, I get something that looks like this. Now, you'll remember that I said everything that used to be dealing with x changes to a y. So this has a vertical asymptote at x equals pi halves. So it's going to have a horizontal asymptote of, we're going to have a y equals negative pi halves and a y equals positive pi halves. Okay. And what do you notice about all of the slopes on the tangent inverse? Always positive, which, whoops, let me slide this over. That's always going to be positive. And what do you notice the further we go out? Yeah, the flatter it gets. Okay, the more horizontal it gets. So the closer the slope should be to 0. So if we plugged in 100 into this, we'd get 1/10,001st for a slope. I mean, it would be very, very flat. Okay, never actually flattens off, but it just gets flatter and flatter and flatter. Okay, any questions? Okay, let's flip the page over then and let's take a look here. We're not going to take the time to derive every one of them. We just found the derivative of sine, cosine, and tangent. We use those quite often. Okay, secants and cosecants, they come up occasionally, but take a look here. So there's sine and cosine. You'll notice that memorizing the sine gives you the cosine. It's got a negative in front of it. Notice the tangent. That's kind of nice. No square roots or anything like that. And take a look at the cotangent here. How are they related? It's got a negative in front. So you'll notice that every one of the cofunctions has a negative. Not surprising there, or at least it shouldn't be. Okay? If you get the sine memorized, you've got the cosine. If you get the tangent memorized, you've got the cotangent. And I'll give you this. These take a little while to get used to, but the derivative of secant is, again, no co in front of it, so it's positive 1. And then the bottom is x square root x squared minus 1. Okay? So you'll notice that the denominators on every single one of these are completely different. Okay? There aren't any similarities here. Okay? With tangent and cotangent, it's 1 plus x squared. With sine and cosine, it's 1 minus x squared. And with secant and cosecant, it's x squared minus 1. They kind of change places and change signs, if you will. Okay? So don't care how you remember it, but you've got to make sure that you've got those memorized. Okay? You might want to think about and consider the domain restrictions on each one of these. The domain restrictions for this one are from -1 to 1. Same for the two of these. Any domain restrictions on this one? Nope. All reals. Okay? From -infinity to infinity on that one. Domain restrictions here? This one's a little interesting. You've got division and you've got even roots, so you've got to be pretty darn careful about what you plug in here. We can't plug in a 0, right? We also need to make sure that we're taking the square root of a positive number. So whatever we plug in for x, it better square to be something that is bigger than 1, if you want to think of it that way, okay? Which would be anything bigger than 1 will square to be bigger than 1, and anything smaller than -1 will square to be bigger than +1. So it's -infinity to -1, not including those endpoints, and then it starts up again at 1 and goes to infinity. It might be worth time looking at the graphs of the secant inverse and cosecant inverse, just to kind of consider why it looks that way, and why that would have to be the domain. Okay. Any questions? Okay. Good. We got 10 minutes left and we got about 6 problems. I do have something down here at the bottom that says, if you would, before the next class section, review the properties of exponentials and the change of base formula for logarithms. So properties of logarithms, change of base formula for logarithms, properties of exponents. There's a reference page at the back of the book where you can take a look at that. Okay? So what we're going to do here is we're going to find the derivative of each one of these. And if we have time, we'll clean it up. And if not, I'll leave that to you to clean up. So if I'm going to find the derivative here, let's see, cosine inverse. It's going to be -1 over big square root, and it's 1 minus something squared. Again, think of that variable here as like a placeholder, okay? So when we carry out the chain rule, it's going to be write down the derivative of the outside, -1 over big square root, 1 minus something squared. What is that something? X squared. Okay? Done? Why not? Chain rule. Chain rule. Okay, watch please. Please don't make this mistake. Don't start cleaning this up and then say, oh, I need to find the derivative of x to the 4th and get 4x cubed here. That is not right. Okay? Would that be leaving the inside alone before you carry out the chain rule? No, it wouldn't. Okay? So please don't do that. Okay? Look at this right here. Look at that blob that you just plugged in there, or look at the original function with its inside. The outside is cosine inverse. I found the derivative of cosine inverse. I've left the inside alone. Now it's time to find the derivative of x squared, so that's 2x. So if I were to clean this up, negative 2x, square root 1 minus x to the fourth, and that's about as clean as it gets. Again, the thing that increases the speed here is having these memorized. 1 over big square root 1 minus something squared. What is that something? Square root of x times the derivative of that something. So that's going to be 1 over 2 times the square root of x times the derivative of x, which would be 1 if you wanted to carry out the chain rule completely. Okay. So what I'd have here is 2 square root x, square root 1 minus x, right? I suppose I could slide that underneath there and write it this way. Might be advantageous to have it written like that. Any questions? Hey, you might want to consider the domain restrictions on each one of these because they'll probably ask for that. So you'll remember that whatever we have here has to be less than 1. So when is x squared less than 1? So think about what we do here. We take the square root of both sides, if you wanted to think of it that way. Or you could graph a parabola and figure it out that way. There are lots of different ways to figure this out. Okay? But it comes down to this. It's between positive 1 and negative 1. Any number in between there would be okay. So it would have the same domain restriction. It would be from negative 1 to positive 1, not including those endpoints. Let's think about this right here. Think about the original function. It's got a radical in it. Okay, you're automatically limited to this. You've got to plug in positives. Then we're going to have a radical in the denominator, so we're definitely going to get rid of the 0. That's not going to be included. And what's the biggest number you could plug into this? A 1. Okay, so finding domains of those is a little bit on the tricky side. Okay, any questions? Okay, all right, so let's take a look at this problem right here. What rule would I use here? Use the product, first and second. So g prime of r is going to be the first times the derivative of the second. Derivative of tangent inverse is going to be 1 over 1 plus r squared. 1 over 1 plus whatever we were taking the tangent inverse of squared. If you wanted to emphasize that, you could put that in parentheses. Ought to carry out the chain rule, or at least consider that. That would be the derivative of r with respect to r, so that would just be a 1. And then plus the second, so this is going to be tangent inverse of r, times the derivative of the first, so that's going to be 2r. And then again, we'd want to clean this up just a little bit. Cancel those. So we get a 1 plus 2r tangent inverse r. Not too shabby there. This was on a test and you had no clue what you were doing. What could you at least write? Because it's a co-function, an inverse co-function, it's got to be negative. And all of these are fractions, so negative 1 over. If you need to look up above, go right ahead. Okay. It's going to be something outside, square root, that same something squared, and then minus 1. Let's go up and take a look. Okay, again, negative. Whatever this was that we were taking the cosecant inverse of, that goes on the outside, and then underneath the radical, it's that same thing squared. So let's see what we've got here. E to the t, e to the t. Done? Nope, because now we have to carry out the chain rule. Now we're finally getting to differentiate the inside. That's going to be e to the t. So the cool part about this, negative 1, square root e to the 2t minus 1. You may want to think about domain restriction. What's that? Oh, it is. Yes, thanks. That's going to be an e to the t. What's going to be negative? No, I canceled them. I canceled them. Okay. Any questions? again, I'll leave it to you to think about what the domain restrictions could possibly be on that one. Let's take a look at the next one. Got to be positive. Big square root. If this one here was that thing squared minus 1, this is going to be 1 minus that ugly mess squared times 6x plus 2, and I'd put that in parentheses. Okay, and this one here is kind of interesting. Let's take a good look at that. Again, you can clean that up, right? Okay. Let's take a look at this. Cosine of sine inverse of 3x squared. Let's see. Outside function is cosine, so that's going to be the sine, negative sine of, leave the inside alone, sine inverse of 3x squared, times the derivative of the inside, so that's going to be 1 over big square root 1 minus whatever that is squared, so that's going to be 3x squared, times 6x. Okay, well this much we can deal with, right? Again, you'd want to consider domain restrictions and all that sort of stuff, but let's take a good look at this right here. Shouldn't those undo each other? Yeah, assuming that we've got the right domain and range and all that sort of stuff, then we should end up with 3x squared here with a negative out front. So our answer should be negative 18x cubed over square root 1 minus 9x to the 4th. You with me there? Okay. I've got like 30 seconds left, so check this out. What if we drew a picture for this? That's the adjacent, that's the opposite, that's the hypotenuse. So this is 3x squared, right? And the hypotenuse is right here, it's 1. What's this side? Square root of 1 minus 3x squared, so that would be 9x to the 4th, correct? Okay. You with me? What's the cosine of that? What's the cosine of that picture here? So I'm going to change color. It's the adjacent over the hypotenuse, right? So this would be square root 1 minus 9x to the 4th. So this expression right here is the same as that expression right there, yeah. No, because it's sine inverse. It's not the reciprocal. Sine is always the opposite over the hypotenuse. Cosecant? Yeah, okay. So, see this expression right here that I've got circled? That's exactly the same expression, right? Watch what happens if I find the derivative with respect to x out in front of that. Okay? What's the derivative of a square root? 1 over 2 times that same square root times the derivative of whatever we were taking the square root of, right? Derivative of 1 is 0. What's the derivative of negative 9x to the 4th? Negative 36x to the 3rd, right? Cancel this with that. What's on the top? Same thing. Could have done it either way. Okay? Again, think about domain and range and all that sort of stuff, but pretty darn cool that wicked nasty trig functions like that, inverse trig functions, and that whole quasi-reciprocal relationship produces stuff like this. And it works perfectly. Whether you do it, we did a bunch of algebra and trig first, then did the calculus, which again usually is easier, or just blindly go through and do the calculus. As long as you carry out the chain rule correctly, you got it right. Okay? All right. Let's see. Please take a look at that quiz. Ben, your quiz is up here. Look at those solutions. If you've got any questions, I'd be happy to go over them. That's what part A of the test on chapter 3 is like. It's going to be 10 problems like that. If you can find the derivative and simplify it to a